Hey guys, Mr. Palmer here. We're going to do another review. This is back with part 4 of our conservation of energy review problems. This one is involving work and friction. That is, an object is having friction do work on it and changing its kinetic energy. So in this case, we're having a car that's traveling. It's going to be coming to a stop over a distance of 50 meters. So let's dig into this. We've got the 50 meters as our distance. It's got a mass of 2,500 kilograms, initial speed of 10 meters per second, and then it's coming to a stop as our final velocity, right, 0. And we're looking for the coefficient of friction. So the coefficient of friction, the coefficient of friction in here, right, that's our mu that we're going to be looking for. Well, this is going to be a work equal to change in kinetic energy problem, right? EK. So our kinetic energy is coming from 1/2 mv squared. You see we're initially at a velocity of 10 meters per second, and our final velocity over here at a stop, v final, is 0. So if I was to do this, I know that my kinetic energy final is going to be 0 minus my kinetic energy initial. And so in this case, we're definitely going to wind up with a negative value for the initial kinetic energy. We're going to start in this case by taking a look at the calculation of this kinetic energy right here. We're going to need to do that first, because if we look over here, here's our work. We can't find that. Right? We have a distance, 50 meters, but we don't know what the force of friction is, and friction is what's going to be slowing this down. So we're going to start by finding this final kinetic energy here, rather this initial kinetic energy. So the EK is equal to 1/2 mv squared. Let's substitute in our values. 1/2, the mass is 2,500, and we're going to be multiplying that by the velocity, 10. That needs to be squared, right? So that's going to be 100, right? 10 squared times 2,500 times 1/2. That gives you a big number, 125,000 joules. Now it's important to notice, remember, this is the initial kinetic energy, the final 0. So if we want to find the work is going to be negative 125,000 joules, or 0 minus 125,000 joules gives us our work. So now that we found the work is equal to force times distance. And in this case, what's doing the work is friction. And it should make sense to you that this work is going to be negative, because friction is always a negative force. It's acting in the opposite direction. So we can either keep that negative there, we can get rid of it. It's just really telling us the sign or direction. We don't really need it to solve the rest of this problem. So let's substitute in 125,000 joules is the work, is equal to the force of friction times the distance. The distance was given to us in the problem back up here. That's the 50 meters. So if 50 meters is our distance, that gives us a force of friction of 2,500 newtons. That's our force of friction. Now that's not what this problem is asking for. The problem is asking for a coefficient of friction. So we need to kind of take the things that we've learned in the past and apply them here. The force of friction we know is equal to mu Fn. And we've always been doing things on a flat level surface. So in that case, we know that the normal force is really equal to the weight. So we've always used mu mg. That wouldn't necessarily be true if we were on an angle, or we were pushing down on this, or there's some other force involved. But on a flat horizontal surface, we're just using mu mg to find our solution. So now we've got enough information we can substitute. Our force of friction is 2,500 newtons, equal to the coefficient of friction, mu. We know that the mass is 2,500 kilograms, and g is 9.8. Now if we solve for mu, it's going to give you a value of 0.10 something, which we can just round to 0.10. Okay? Now I know that's a lot. It's taking some information that we had back here with our work energy theorem, right? It's applying what we learned about work here, and it's also going back and adding some information about friction. It's really a 3-step problem that we have to have. It's pretty complex, but if you go back through and identify each one of the components, it really can be simple. All right, I'll be back with one last review problem in part 5.